outsider when it comes to robotic engineering. So I'm going to present a little bit more of the overview of Roboat, a little bit of an introduction into the MIT Sensible City Lab, and then my colleague Jonathan is going to go much more of a deeper dive into the robotics and automation of the project. So yeah, so we're talking about Roboat, which is, I think the name is also kind of unique, robotic boats. And it's one of our largest projects at the MIT Sensible City Lab. We have a team of over 40 researchers. We come from various different backgrounds, so mathematician, physicist, but also computer scientists, data scientists, urban planners, social scientists, and it's a real mix of disciplines and also cultures. And it's led by Professor Carlo Ratti. We also have a large intake of Italian students, and we work on several projects. We have projects based on environmental data, projects based on social segregation and gentrification. But like I said, our biggest one is probably the Roboat project, which is a collaboration between the MIT Sensible City Lab and the AMS Institute, which has been running for 5 years. And the project is based in a very complex environment, which is the Amsterdam canals. The canals these days are mainly used for social boating and tourists, but historically they were a really huge part of the urban fabric in terms of logistics. But over time, this has shifted to the streets. So what we're trying to achieve with Roboat and digital technology is trying to bring back this importance to the canals of Amsterdam by creating the first fleet of autonomous vessels. And I'm just going to play a very short video explaining a little bit more about the overview of the project and also the 2 full-scale prototypes that we've built.
This is Lucy. Lucy is a rowboat, a fully autonomous, zero-emission boat that operates on urban waterways, and she can change the way cities work. As congestion and emissions continue to rise, while cities continue to grow, the existing infrastructure of many cities struggles to keep up. Rowboats offer a solution by moving road traffic to the water. By bringing passengers from A to B, or as an on-demand boat, taking you anywhere you want. And they can also help the city as a multi-purpose workboat. Take Crystal. She is equipped to collect household waste to free the streets from heavy garbage trucks. Rowboats are fully autonomous, so they navigate without a skipper and can operate 24/7. In order to sail by themselves, rowboats need to perceive their environment and recognize objects such as bridge pillars, floating objects, and of course, other vessels. The primary source of information comes from a LiDAR sensor, but rowboats are also equipped with cameras, GPS, and a digital compass. Roboat's onboard computer combines and processes all of the data and runs the rowboat software so it can successfully complete its mission plan. After 5 years of development, testing, and experimentation, we have now successfully enabled autonomy on the full-scale prototypes. Roboat is ready for the next step. Join us and let's unlock the potential of urban waterways together.
Yeah, I mean, as the video mentioned, there's some various urban functions that we've been creating with the platform. One of which, of course, is moving people, having Uber robots, but also in terms of moving goods and deliveries, we could create on-demand Amazon lockers, for instance, throughout the city, which would then remove the need for these large delivery trucks in Amsterdam, causing congestion and high emissions. But also one interesting user case is actually using these boats to create on-demand infrastructure and dynamic infrastructure. Instead of having these high infrastructure costs of creating bridges and platforms, these boats can actually start responding to human behavior in real time. So depending on where human traffic is starting to form, these bridges can help alleviate this congestion. And one of our more developed user cases, I would say, is actually using Roboat to actually start collecting trash on the edge and bringing the trash to the incinerator. So actually, again, similar to the goods and services removing this need for the delivery trucks, this is actually also removing the need for trash trucks, which are a large contribution of emissions throughout the city of Amsterdam. So what would happen is people would drop the trash into Crystal, into the port, and then it would autonomously drive to the incinerator and then constantly be collecting throughout the canals. And this video will also explain the user cases for waste management. And if you can really think about the Amsterdam streets, if you remove delivery trucks and trash trucks, these streets start to become a lot more livable and usable for street life. Put a little bit more back into the robotic engineering, and we were doing many tests through the first 4 years in the MIT pool. This is us testing the highly used quarter scale. I think we built over 50 of these little boats, which allowed us to test not only different configurations and shape shifting, but also it allowed us to test the navigation. And what we did in the MIT pool was to avoid not only fixed objects, but dynamic objects. And if you're an MIT researcher or any robotic engineer, I would promote that when you do these algorithms, that you put yourself in danger. So you, on the left, you see these two static bins. And then this is one of our researchers, Wei, who was brave enough to put himself on the line to avoid the robot. And luckily his algorithms had worked successfully not to take his head off. But this is just a very brief introduction into what Jonathan will take a deeper dive into. And these boats are basically sensing platforms at the same time. It's not just the case of moving from point A to point B or creating an urban function. It's also a case of trying to utilize the various sensors that we have on these boats for also social good. And one of the key ones that we have is actually a water quality sensor that we've embedded into the boat, so we can start collecting hyperlocal water pollution data to start being able to clean the pollution in the canals of Amsterdam. I'm just going to finish on this video, which again is a bit of an introduction into how these boats perceive and navigate through a complex environment such as the canals of Amsterdam. It uses a combination of LiDAR and computer vision. The LiDAR is just being able to extract distances, and then if you combine that with object segmentation and detection, you're able to understand if it's a boat or tree. And like I said, these boats are sensing platforms. So one user cases to understanding or utilizing LiDAR data is maybe to analyze the structural deficiencies of bridges, or in such a unique context of Amsterdam where you have these 17th century houses on the side, we can actually start to see over time if these facades are starting to shift, creating a bit of an early warning system to structural deficiencies throughout the city. You can also start analysing the ecology of trees, understanding when these leaves start falling off at certain times of the year. So it's really trying to open up more aspects and more questions. What can we do with the data that we collect from Roboat for social good and making our cities more livable? Okay, I'm going to pass to my very talented colleague Jonathan, who is going to take a deeper dive into the more robotic automation side.
Perfect, Tom. Thank you. Let me take over from here. 1 second. I think I'm not visible anymore. Is this possible? I think it automatically turns off, so we'll have to do with this. You can see my screen now, right?
Yeah, we can see it.
Perfect. So thank you, Tom. I'll take over from here. My name is Jonathan, and I'm part of the Amsterdam Roboat team, which is part of the AMS Institute, Amsterdam Institute for Advanced Metropolitan Solutions. And within AMS, we are part of the mobility and logistics track here at AMS. AMS is located in the city center of Amsterdam. Can you see my mouse, by the way? Is that visible?
Yes.
Yes, we got it.
Perfect. So I will point at a couple of things. So this is the AMS building over here. And if we take a closer look, we have this nice section of water, which is actually a private area. So we can use this area to test our full-scale boats because we have a nice yellow crane installed half a year ago. So right now I'm sitting here in the second garage door, and whenever we go out testing, we just push the boat out and take the crane and put the boat in the water. It takes about 10 minutes. And that allows us to very quickly validate all the software that we wrote for the boat, which is very convenient. I joined the project back in April, so roughly 8 months ago. And when I got here, Pietro, the designer of the boat, had the privilege to christen the first full-scale boat, which is called Lucy. And this was really the start of the testing period of the full scales. Tom mentioned that a lot of testing has been done on those quarter scales, as we call them, the smaller boats. But the end goal of the Roboat research project was to have full scales operable in Amsterdam. So I joined at a very interesting time, which was 6 months ago. I joined a team of 3 guys, which you can see here on the platform. And we are very well coordinated, as you can see, because we are trying to find where north is, and we cannot agree. But I will introduce each one of them, and then a quick introduction of myself. Well, on the left, that's obviously me. And then next to me is Rens. He is a mechatronic engineer. He laid down most of the groundwork for the electronic system in the boat. Then next to him, with a nice Italian red wine, is Joshua. He's a software engineer from New Zealand. He joined the project about a year ago. And then next to that, you see my boss, actually. He's called Inse Dynama, and he's dressed up as Poseidon to give his blessings to Lucy. And that's me on the left here. Jonathan Klein Schiphorst, as mentioned. I graduated from the TU Delft in systems and control engineering back in March, and right after I could join Roboat here as a control engineer with a focus on software. So Josh and I are the software team. So my boss Inse Poseidon, he is not always dressed up as Poseidon, but he is also the project lead. And back in October, we had the Roboat demo days, as you can see here, where we showed off the capabilities of our 2 full-scale boats. Was a great event. Let's see, where are we? Yeah, let me first give a hardware overview of the boat, in case you're not familiar. So this is Lucy. And what is interesting about Lucy is that she has a universal hull design. And that means that our other boat, Crystal, is equipped with a garbage module, but the hull design is exactly the same. So we can switch the use case of the boat by simply switching out the top deck, which is fairly easy to do. So we have a multi-purpose boat, which can be used for several use cases. More on the hardware side, we have a 10 kilowatt battery, which lasts us over 24 hours of operation. And we can even put a second battery in to allow for even longer durations. For the drivetrain, we have 2 main thrusters, which are torpedoes. They are pointed forwards. And next to that, we have 2 bow thrusters, which are pointed sideways. And this allows for holonomic movement, which is very convenient, for example, when docking. More on that later. Next to that, we have a latching system installed, which are mechanical arms that allow the boat to autonomously dock and latch on to the wall. And then the these brakes are passive, so the battery can turn off and it can charge itself via capacitive charging. A very nice feature to have. And other than that, we have a range of sensors. A couple of them are illustrated here. So we have a LiDAR. In the black box here is a camera and an IMU. And we also have 2 GPSs for localization. And of course, what is the goal of Roboat? It's to autonomously move from point A to point B while avoiding obstacles. And we can put Lucy as an agent which has to interact with the environment, in this case the marine terrain here in Amsterdam, and she can do that. She can sense the environment or her state through its sensors, and she can operate in the environment through the use of her actuators, and she can take action in that. And what's important here is that the boat is, of course, autonomous. So let me run you through the software stack, how we do this. So any regular boat with a joystick or with manual controls will have a hardware interface and a UI through which you can interact with that. So let's say we have a boat with these 4 thrusters. We can steer her with levers that determine the thrust delivered by these thrusters. However, we want to sail from point A to point B autonomously, and therefore we created the following software stack. So instead of putting these forces manually in to the system, we provide a waypoint, as we call it, to the coordination layer of Roboat. This waypoint is then passed on to the global planner, which is sort of a Google Maps for the waterways. So this will determine a rough path of which is away from point A to point B, as you would get it on Google Maps. And this map is a static map, but of course in the environment there are dynamic obstacles which we need to sense. So this global path is passed on to a local planner, which takes the LiDAR data, constructs a map of obstacles, and then plans around it, such that we get a feasible path. This path is then passed on to the controller, a nonlinear model predictive controller, which I will go into more detail later. And that controller calculates the forces that are needed to realize such a path. But we want to do this autonomously, of course, and that is why we use our sensors, which are passed on to our filter stack to sense its environment and plan around and provide the needed forces to fulfill such a path. And these filters, they take the sensor information from Lucy and map it to more useful information. For example, here this arrow represents the odometry, which is passed on to the controller. And for example, the obstacle map created by the LiDAR is passed on to the local planner in order to plan a path around it. And this way we can really take the human out of the loop and make the boat sail autonomously. Since you are control engineer students, I will go a bit deeper into the controller that we use and the filter we use for localization. And for that, we need a model of the boat. So I'll run you quickly over that, and then let's have a deeper look at the controller and the localization filter. So the model we have of the boat consists of 6 states. The first 3 are in the map coordinate frame, as you can see here. X is pointing forward, Y is pointing to the right, and the yaw is, let's see, clockwise. So Z is pointing inwards the screen. And this is the first 3 states of the rowboat in map coordinates, and we transform these coordinates into boat coordinates with this rotation matrix R, and that provide so the derivative of the first three coordinates is given by this rotation matrix R times this second state vector V, which are the velocities in both coordinates. So U is velocity forward, V is velocity sideways, and R is the yaw rate. And this rotation matrix is just a simple rotation matrix, as we all know it, that provides us with the first three states of the boat. Then the second set of states is a bit more involved. These are determined by a similar equation as the manipulator equations. I assume you are familiar with that. The only difference is that V is already the velocities here. So V dot is the accelerations, and other than that, it's the same. And what really what I found surprising when I started this project is how simple this model is, yet how effective it is. So the mass matrix here is just a diagonal matrix with the mass terms on the diagonal. The Coriolis term here, we actually ignore it. So this is 0. And the damping matrix is also just linear terms, which to me was surprising at first, since hydrodynamic drag scales with velocity squared. But since we are operating at low velocities, this quadratic term does not dominate yet. We usually sail around at approximately 3-4 meters kilometers per hour. So a linear term for this damping matrix is perfectly fine. And it's again a diagonal matrix with the damping terms on the diagonal. Considering that we have this torque here on the right, not torque, the forces in the x, y, and in the u, v, and r direction. And since we have these 4 thrusters, which I showed you later, our B matrix is also fairly simple. So forces 1 and 2 are come from the main thrusters, which are pointing forward. So multiplying this vector with this matrix here on the left results in a force pointing forward in the boat frame of reference. Then the third and the fourth force are the bow thrusters, which point sideways. So multiplying that with this B matrix, you can see that these forces ensure that there is a force applied in the V direction. And then for rotation, all 4 thrusters have a part in that, and it's just the force of the thruster multiplied by the arm, and the arm here is A/2, which is half the width of the boat, and here B/2, which is half the length of the boat. And yeah, with such a simple model, we can already do amazing things. So let's see. Yeah, if you shuffle the equation above around a bit, you get the second state of Roboat. That brings me to the full 6-state model we have. So again, x, y, yaw in map coordinates, and u, v, r in boat coordinates. And the dynamic model is slightly nonlinear because of those first 3 terms, but the rest of the model is actually linear. And this is just a summation of what I just explained. With this model, we deploy our control strategy with this, which is nonlinear model predictive control. I hope you are familiar with model predictive control. Otherwise, I will give a very brief overview, which I hope is clear. So in order to determine which forces the thrusters need to give, we have a optimization problem with the u as the decision variable, and the equation to be minimized is this cost function j here on the top, which consists of the the states and the future states of the boat and the control inputs over the control horizon. And this optimization problem is subject to a couple of constraints. So we have the dynamic constraints over here. So wait, let me first give a better overview of what model predictive control actually is, which is shown here. So model predictive control at each time step, here time step k, calculates a predicted future of the boat's trajectory and tries with the decision variable u to minimize the error between the reference trajectory and the predicted trajectory. Then if the optimization is completed, the first control input is applied. The horizon is shifted to the right by 1, and we do this whole optimization again. And this way we can have optimal control with state constraints and input constraints. So coming back to the equations here on the left, this J is the cost function to be minimized, and which is subject to the model dynamics, the initial state where we are at that time step, and also to some state constraints and input constraints. For example, we have a maximum torque on the thrusters, which need to be adhered to, otherwise they will overheat and destroy themselves. So that's not nice. And using this model predictive control framework, we can ensure that the forces are never higher than we want them to be. And then state constraints, for example, can take into account obstacles in the map, which states cannot be visited, otherwise you will bump into something. And this needs to hold true for all tau, which is the prediction horizon, which goes from t to t plus capital T, and we use a prediction horizon of around 6 seconds, which is plenty. Now this cost function is nothing too complicated. It might look a bit overwhelming at first if you are not familiar, but let me run through it. So it is an integral from time step t to time step t plus capital T, which is the prediction horizon, and it captures a quadratic cost function f, which is just the error between the reference trajectory and the predicted state times a Q matrix over here, and we have quadratic cost on the control input over here on the right as well with R. And then for stability reasons, we have a terminal cost, which is E, which puts an extra cost on the last state it visits. And these Q and R matrices are hand-tuned. Takes a bit of time, but it's also very intuitive. So if your boat is not going fast enough, for example, you just up the element that works on the velocities of the boat, and so forth. And so enough equations. I'll just show you what it looks like in sim, which is like this. Over here you can see the boat in our simulation environment. The green line is a series of poses, which is the path that is given to the robot, and the purple line of arrows is the predicted output. And as such, we can move through the water and follow the line we give it. Next up, I wanted to talk a bit about how we do localization, which we do with an extended Kalman filter. I presume the Kalman filter is known by control students. The extended Kalman filter is a nonlinear version of the Kalman filter, which linearizes the the model around the current predicted state, and then applies the prediction step and the update step accordingly. What is nice about the framework we use, which is ROS, in case you were wondering, is that we can use external packages. For this localization, we use the excellent Roboat localization package provided by ClearPath Robotics. It is designed to fuse an arbitrary number of sensors, which in our case are an IMU and actually 2 GPSs. I think when I got here, there were already 2 GPSs on the boat. On the quarter scales, they had a single GPS, but they had a lot of trouble with getting accurate heading for the boat, since the IMU is very prone to drift, and it was not sufficient enough for our use case. So the engineers at MIT decided to go with 2 GPSs, from which we can then calculate a normal vector, and that can be used to calculate the heading. Let's see. So this package provides a 15-dimensional state estimation of the Roboat. The first 6 are X, Y, Z, roll, pitch, and yaw. Roll and pitch we are generally not too interested in, but X, Y, and Z also not, because that's of course determined by the height of the water. So from this we take the X, Y, and yaw. It also estimates the linear and angular velocities. Again, the Z dot, roll rate, and pitch rate are not too interesting to us, but X dot, Y dot, and the yaw rate are. And lastly, to make it 15-dimensional, it also provides linear accelerations, which is very convenient. Some insights on some difficulties that we have at the moment is that these sensors we use, so an IMU and 2 GPSs, is not always good enough at this moment in time. You can imagine, for example, sailing under a bridge. You will lose the GPS signal quite quickly, surprisingly quickly, actually. In which case the odometry cannot be calculated anymore. So for that reason, we are currently looking into fusing LiDAR and/or camera data into the mix to provide a more robust state estimation. Let's see, where are we at? Ah, yes. So this is a screenshot of our simulation environment. As you can see, this is the marine terrain just outside here, and all the sensors we use are simulatable, which is very convenient since we can test most of the software in simulation before we have to go out into the real world. And with that said, yeah, we're currently at a very interesting stage of this project. So we have boats that are able to sail, as you can see in the last part of this video, which Tom skipped. But we are able to confidently sail around in the marine terrain, avoid obstacles such as the platform you see in the back. And but a lot has to be done as well in order to make these boats fully operational. But exciting times ahead, I would say. So the next challenge for Roboat is really go into the canals, make the miles, and make the boat safe and usable in the urban area. And for that, I have a small call to action. We are always looking for talented students who have an interest in what we do. So if you like this project and you want to collaborate with us through an internship or a thesis project, please send us as a message at info@roboat.org. Interesting topics could be, since you are control and automation students, perception, navigation, simulation, or other things. If you have an idea on how to improve Roboat, what to do with Roboat, please shoot us a message, and maybe we can figure something out. And I took a look at your syllabus. Some courses which would be interesting, I think, for you is perception, localization, and mapping for mobile robots, automation and control in vehicles, simulation techniques and tools, and also multi-agent systems, since these robots could collaborate together, for example. I hope that was all clear. And that concludes the talk. I think now it's time for questions. So let me stop sharing and turn on my camera again.
Thank you very much. That was extremely interesting. Also, most of the things that you said, we actually studied them, but we've never seen them in a complete project. So that was really, really interesting. If someone has questions, please write them in the chat. Also, from the room, if you have questions, just tell me. Also in Italian, I can translate. I have a first question.